Hello all, myself Professor H.A. More, working in All India Sri Shivaji Memorial Society's Institute of Information Technology, Pune, in Department of Engineering Sciences. Today's topic is the second law of thermodynamics. Before this session, we have learned the basics of thermodynamics and the first law of thermodynamics with their limitations. In this session, we'll see the basic terminologies to learn the second law of thermodynamic statements, and the concept of heat engine, heat pump, and the refrigerator. So, to start with the second law, so while learning the first law, we have some limitations. If you see this cup of tea, so in this hot cup of tea or coffee, so it is as per the nature, as you know, it transfer the heat from higher temperature to the lower temperature. That is from cup of tea, which transfer heat from um, system to the surrounding. So heat lost by the coffee is equal to heat gained by the surrounding. As per the first law, it is satisfied. But converse, it is not true. That is, heat taking out from the surrounding is not equal to the coffee getting hot. Means whatever heat we are supplying to the system to process a coffee or to make the hot coffee, the heat supplied to the system from the surrounding is not equal to the heating of the coffee. So still first law of thermodynamics is satisfied. From these days, day-to-day life examples, it can be clearly seen that satisfying the first law of thermodynamics does not ensure that the process will occur actually. The process proceeds in certain direction, but not in reverse direction. That is from low temperature to the higher temperature. The first law has no restriction on the direction of the process to occur. That is one of the limitations of the first law of thermodynamics. To overcome that, so we have the second law of thermodynamics. How we can convert the low temperature body to the higher temperature with the supply of energy or the work to the system. So there are some significance of the second law of thermodynamics. Second law of thermodynamics is not just limited to identify the direction of process. It also asserts that energy has quantity as well as quality. Third, it helps to determine degree of degradation of energy during the process. It also used to determine theoretical limits for the performance of the commonly used engineering systems like heat engine, refrigerator, heat pumps, etc. So this is the significance of the second law of thermodynamics. So if you go ahead, so we can say second law deals with the direction of the heat as well as limiting or converting of heat into the work or vice versa. That is the mutually converter of heat and work over to heat. Okay, so there are depends on the concept of second law of thermodynamics with respect to the conversion of heat into work and the direction of heat flow from low temperature to the higher temperature. There are two scientists who worked on this, that is the Kelvin Planck and the Clausius. We'll see those statements later on. So before that, we should have some concept of thermal equilibrium. If two objects are at same temperature, if two objects are not at same temperature, then heat will be always go from high temperature body to the low temperature body, or high temperature object to the low temperature object. So hot object will always decrease in temperature and cold object will always absorb the heat from the high temperature body until they are at same temperature. That is called the thermal equilibrium, means the steady state occurs in that particular system. So there are some basic terminologies to learn the second law as required. The first one is the heat reservoir. So heat reservoir, as you see, so heat reservoir is the reservoir or the system which is having the abundant amount of energy, that is the infinite amount of energy. And if you take the finite amount of energy from that system, there will not be effect of that particular system. So if you take the bucket of water from the river or ocean, there will not be effect on that particular ocean or the river on their temperature or other properties. So what I can say, this is there are examples of heat or thermal reservoirs are large water bodies like sea, river, lake, and the atmosphere. You can see in the picture. So self-explanatory picture is there. Now next concept is about heat sink and the heat source. What is heat source? The system which supplies the heat to another system or high temperature reservoir is called the heat source. And next one, heat sink, a system which absorbs heat from the system or a low temperature reservoir is called the heat sink. So if you see this picture, in this picture, if you find there is one heat source on the right side, and on the left side there is a heat sink, and in between there is a work system. So heat is transferring from the high temperature reservoir to the low temperature. This ice cube is transferring the heat, that is absorbing the heat, and heat source which is transferring the heat to the system. The heat source which supplies the heat to the another system, and heat sink which absorbs the heat from the another system. So to understand the concept of the heat refrigerator and the heat pump, we should know first of all that is heat engine. Heat engine is the thermodynamic system or a device operating in a cycle to which net heat is transferred and from which net work is delivered. Means if you see the heat source in the right side diagram, if you see correctly, this is your heat and this is your heat source and heat sink. Heat source at higher temperature and heat sink at lower temperature. And due to the heat source which supplies to the system, in case of the boiler is getting the heat from the system and which is producing W amount of work. So that W amount of work we can calculate heat supplied to the system minus heat absorbed by the heat sink. So QH minus Q low or Q high minus Q low. So heat engine is the power producing device that converts heat energy into the mechanical energy. So there are some systems are in the day-to-day lives. So there are boilers, automobiles, tractor, aircraft, ships, etc. are which are producing power in the system. That means IC engine or external combustion or internal combustion engines are the examples of the heat engine, which are the prime movers and which are producing the heat. Okay, next to that, if you see the schematic view of the steam power plant, which is producing W amount of work after getting the Q in, that is you can see there's with the help of pump we are supplying water to the boiler. Water is converted into the steam. That steam is nothing but Q in amount of heat, and that Q in amount of heat, that is in the form of steam, it is impinged on the turbine blades, and that turbine blades are producing W amount of work. And that W amount of work, after getting W amount of work, the heat is rejected, that is the Q out to the condenser to the sink, and again that cycle is completed. So if we go ahead as per the law, we can write what is the work net. Net work is the or net work output is the whatever Q in we are taking minus Q out or Q out W out minus W in. So here the set of components and no mass flow in and out of the system. And in the closed system, if it is there, internal energy produced inside the system is a 0. That we can write W net, that is the work net, is equal to Q out minus Q in. Rejected heat to the condenser by the condenser is the heat sink and the boiler is the heat source or the furnace, which produce the work net, that is the W net is equal to Q out minus Q in. So as per the first law, if I want to write the performance of the steam power plant in terms of efficiency, that is, efficiency is output divided by input. In this diagram, if you see the diagramic way, in this the W amount of work, that is a work output, that is a net work output. Okay, so net work output and rejected heat, that is total amount of heat supplied to the system. So how I can write W net divided by Q in. Q is the heat supplied, that is the heat input, and W net is the work output, output divided by input. That in the same way we can write Q out minus Q in. Work net, we know in the previous slide we seen work net is equal to Q out minus Q in, that is a Q hot minus Q in divided by heat supplied, that is the Q in. You will calculate the performance of the or the efficiency of the boiler or efficiency of the thermal power plant. So Kelvin step, if you go ahead about the conversion of heat from statement as per the statement of Kelvin Planck statement to learn the second law of thermodynamics, you should know, this is most important to start with the second law of thermodynamics, as the Kelvin Planck said that about the work and the heat conversion. They stated that it is impossible to produce a device, or it is impossible for any device to operating in a cycle to receive heat from single heat reservoir and produce the net amount of work. So alternatively, I can say no heat engine can have the thermal efficiency of 100%. Okay, if go ahead. Next is heat pump. It is a thermodynamic system or device operating in a cycle which removes heat from low temperature body and delivers it to the high temperature body. Now, up till now, what we've seen as per the first law of thermodynamics, heat engine was a power producing device because we produce the W amount of work as a work output. And in this case, we are going to supply the work to the system to getting the cooling effect. So that is, it's a power absorbing device. Absorbs heat from low temperature body using work supplied to the system and transfers heat at a higher temperature. There are examples of heat pump, refrigeration, air conditioning systems, chillers, ice plants, etc. So which produce the cooling effect or heating effect depends on the condition. Now next up, how the things are converted. So as per the basic concept of heat source and heat sink, we know the heat source is supplying the heat and heat sink is the absorbing the heat from the system. And in this system, if you see the particular refrigerator is nothing but the which device will produce the cooling effect in the particular area. So there are some components. You can see there are components like this is your expansion device, condenser, compressor and evaporator. So these are the devices which produce the under the vapor compression cycle the cooling effect or heating effect as per the heat pump or refrigerator in the system. So this refrigerator or heat pump's performance we are measuring in terms of COP. What is COP? COP is the coefficient of performance. That is the desired output. What is the desired output? We have to maintain a temperature in the evaporator, that is a QL amount of heat. QL or TL amount of heat into the evaporator as is in the ice zone. And what we are supplying as the input, required amount of heat input is the compressor work, that is a W net. W net we are supplying. Okay. So as per the first law of thermodynamics, we know work net is equal to Q hot minus QL, and work net is net work we are supplying in terms of uh, difference, algebraic difference of q hot minus ql. So if you arrange this, so heating cooling effect divided by work net, that is the COP of the refrigerator, that is the desired output upon required input. So we require to produce the cooling effect in the refrigerator. So COP of the refrigerator is always greater than 1. So heat pump, again the same component, that is evaporator, compressor, condenser and exhaust. This cycle we'll see under the applications of different devices. Right now we are learning the second law of thermodynamics. What is the performance of heat pump we can note? So desired output upon required input. In this case of the heat pump, we require to maintain a temperature at a higher level. That is the QH. The required temperature QH we require to maintain, any energy input or the input will be the compressor work. So what is QH? QH is nothing but we require to maintain, in case of the winter condition, we require the temperature of the room to be maintained higher than the outside. So that is the QH, and work supplied, that is work net QH minus QL, that is Q hot minus QL, or you can say in terms of temperature pH, that is the T hot divided by pH minus PL, or T hot minus PL. So by arranging, we can say COP of the heat pump is equal to COP of refrigerator plus 1. So to revise these statements, we can have the two statements of the second law of thermodynamics, that is Kelvin's law and Clausius statement. It is impossible to construct a device whose only effect is to convert given quantity of heat into the complete work. Then, that is, we have to convert heat completely into the work. Then Clausius statement about the temperature effects. Heat flows spontaneously from hot object to the cold object. Heat will not flow from the cold object to the hot object without input of work. So I can say it is impossible to construct a device about Clausius whose sole effect to convert low temperature heat reservoir into the high temperature reservoir. That is the direction of the flow. Thank you. In this lecture, we learned the second law of thermodynamics and some concepts like heat pump, refrigerator, and the heating. Thank you.